Hello, everybody. Welcome to welcome back to a virtual section of Calc 3. I apologize for missing class last Friday. Turns out I came down with a nasty cold that incapacitated me for a couple of days. I'm feeling a lot better now, though. So this is kind of this video is kind of an attempt to recoup some of what I was going to talk about last Friday, so that we don't get further behind than I'd like to in this class. We're already a little bit behind where I'd like to be by spring break, but you know what? That's okay. In this video, we're going to be looking at a few different things relating to this theorem that we talked about but never proved last time. But in the meantime, I hope you all are enjoying your spring break. You get to do something relaxing, like, I don't know, go to the beach or something. Speaking of going to the beach, what does mathematics have in common with going to the beach? Turns out what they have in common is that they both have tangents. Anywho, in this video, we're going to finish off standard 11, kind of the little bit that I was hoping to finish for the end of class Friday. And when we come back after the break, on the Monday after break, we're not going to do the standard 11 quiz quite right away, because I want to give you the chance to come and ask me about what's in this video first and office hours and such. So instead, on the week when we get back from break, that Monday, we're going to start standard 12, start talking about optimization, finding maxes and mins of multivariable functions. A little bit what we're going to be doing today, actually. And on Wednesday, we are going to do the exam, which will still be over standards 1 through 11, as I said before the break. And then on the Friday after spring break, that's when we'll do the standard 11 quiz, and then keep talking through the rest of standard 12. So that's kind of the plan going forward. So to start off, I thought we'd do a little bit of a reminder of what we were doing in the first half of standard 11, the Wednesday before break. What was going on is we were talking about directional derivatives, which allowed us to find the slope of a multivariable function standing at a point if we were to travel in any direction that we would want to go in, rather than just looking at what's the slope in the x direction, what's the slope in the y direction. The directional derivative allowed us to find slopes in other directions as well. And the general idea is that if we have a function f going from Rn to R, thought we'd start with just a little bit of review. If A is kind of the point on the surface of your function, so A is going to be a point in Rn, V needs to be a unit vector, meaning a vector of length 1. So if you take the square root of V dotted with itself, you just get a positive 1. Then the directional derivative of the function f at the point A in the direction of V, which is the same as taking the slope of your function f. If you're standing at the point A, you're traveling in the same direction that V is pointing, is going to be the gradient of f evaluated at A, dotted with your direction vector V, telling you which direction are you walking. So for instance, this is the example we were looking at last Wednesday, where our function is f of x comma y equals e to the 2y times sine of x. So we have this function here from R2 to R. Okay, we need to update. This black dot is going to represent our point A, and V is going to be this blue vector here, which we're going to treat as a displacement vector that starts at A. And in this scenario, the directional derivative of this function at A in the direction of V is going to be, if you're standing at this point on the surface and you're walking in the direction of this blue arrow, what's the slope going to be? If it's negative, that means we're going to be walking downhill. If it's positive, that means we're going to be walking uphill. And this formula here, we've talked about last time, is sort of the way that you would go about evaluating that. So for this case, this is where the point was at pi over 3 comma 0. V was in the direction of 3, negative 1. And 3 over square root of 10, negative 1 over square root of 10. And we found it had a very small downhill slope when we evaluated this in our example last Wednesday, which I encourage you to go maybe take a second look at. So what I want to do in today's video is talk about how can we find the most uphill direction that we could possibly walk in, or the most downhill direction that we could possibly walk in. So let's take a second and sort of look at what's going on here. So instead of this vector, let's say we wanted to say what would happen if we walked in this direction. Where this direction is going to be the most uphill slope that we could possibly walk in if we wanted to start at this point right here. Dr. Gerstle, the arrow doesn't start, it starts at that point. It's just clipping through the graph a little bit. It's going to turn out we can say something, given an arbitrary function and an arbitrary point, about what's going to be the most uphill direction that we could possibly walk in, and what's going to be the most downhill direction that we could possibly walk in. And what's going to turn out to be the case is this theorem, which I got to state, I think, in both sections at the end of last class, but never got to do anything with. Where, in part A of this theorem, it's saying, hey, if you have a function f and a point A, then the directional derivative, meaning the slope in whatever direction you walk in, is going to be maximized. It's going to be as positive as possible if v, the direction you're walking in, happens to point in the same direction as the gradient vector, the gradient of f evaluated at A. Remember, this is going to be del f del x evaluated at A, del f del y evaluated at A. And if your function's from like R3 to R, you might have a del f del z evaluated at A. If it's from R5 to R, you'll have 5 components in your gradient vector. But it's your partial derivative. Your vector of partial derivatives, it turns out if you were to walk in the same direction as where the gradient vector is going to point, that's going to be the most uphill direction you can walk on, meaning the direction that's going to give you the most positive directional derivative. And if we're walking in that direction, we can say exactly what the directional derivative is going to be. It's just going to be equal to the gradient vector's magnitude. Meaning, if we go back to our graph for just a second, if we were walking up in this direction, the slope we're going to get, like the number corresponding to the steepness, is going to be equal to the magnitude of your gradient vector at that point. And similarly, if you want to look at what's the direction we can walk in that's going to give us the most downhill slope, the most negative slope we could possibly have, in other words, the direction that's going to minimize the directional derivative is if the direction v you're walking in is going to point in the same direction as the negative of your gradient vector. Meaning if it points in the exact opposite direction that the gradient vector is going to be pointing. And if that's the case, then the slope that you're going to get walking in that direction is going to be equal to the negative of the magnitude of the gradient vector. So this theorem gives us a nice way of saying you're standing on any function at any point, what's going to give you the most uphill route to walk, what's going to give you the most downhill route to walk. It's going to be pick the direction corresponding to your gradient or the negative of your gradient vector. And we're going to actually go through and prove this one. At least we're going to prove part A. The direction you walk in is going to be in the direction of the gradient vector, and the slope you'll get walking in that direction, the biggest possible slope you can get, is going to be the magnitude of that gradient. It's going to be equal to the magnitude of that gradient vector. So we're going to go through and actually prove part A here. But before we prove part A, I want to do a quick little bit of review first about something from Standard 2 that we're going to need to use as part of our proof. That being this result right here. Where, let's say you have two vectors, A and B. And what's our formula for the theta, the angle between them? So, let's see. I'm going to start picking on you, even though you're not here. Emily, what was our formula for how we could find cosine of theta, where theta is the angle in between the two vectors A and B. Is that Emily? You don't remember? All right, fine. Who does remember? Lori, glad you remember. What was the formula for cosine of theta? That's right. You had that cosine of theta is going to be equal to the dot product of A and B divided by magnitude of A times magnitude of B. That was another way to write this, to find cosine of theta. So, good try, Emily. You almost got it. So, let's see. Isabel. What would happen if we rewrote this equation and got A dotted with B by itself? What could we say that's equal to if we kind of rearrange this equation? That's right. Good job, Isabel. It's going to be equal to the magnitude of A times the magnitude of B times cosine of that angle between your two vectors, which we could just get from taking this equation and multiplying both sides by magnitude of A times magnitude of B. On the right, it's going to cancel out and just give us A dot B. On the left, it'll get us this magnitude of A times magnitude of B times cosine of theta expression. Yeah, nice job. We're going to need to use this formula here as part of our proof. So let's prove part A here. So here's the idea. Let's say we have a function f. This is a proof of A. If f is a function from Rn to R, and A, is a function, and A is any point in Rn, we need to show that if we're standing on the surface of our function f at the point A, then the steepest direction that we can possibly walk in is if we were to travel, if our direction vector v is parallel to the gradient vector, gradient of f evaluated at A. So that's what we're going to show. Well, if we have a function f going from Rn to R, and A being our point in Rn, we know that for any direction vector v, the directional derivative of f evaluated with A is going to be equal to the gradient of f evaluated at A dotted with B. That was our formula. And for that to work, we need that for a direction vector v, we need that v is a unit vector. But if v is a unit vector, meaning a vector of length 1, then the slope of what we would get if we're standing on f at the point A, walking in the direction of v, is going to be this expression. Now, here's what I want you to think. Let's say we're standing at a point A. So A is going to correspond to this point. Let's say we're going to look at v and the gradient of f evaluated at A as sort of being two displacement vectors that start at the point A. If theta is the angle between them, how could be a way that we could rewrite this expression using kind of this idea over here? Brianna, what's that? You want to replace the dot product with magnitude times cosine of theta? I like it. Yeah, good idea, Brianna. We're going to rewrite the gradient of f evaluated at A, dotted with the vector v. According to this formula over here, we can rewrite that as being equal to the magnitude of our gradient vector evaluated at A times the magnitude of v times cosine of theta. Sorry, I had to erase that. Let's put that back up here. There's our magnitude. There's our gradient. Here's v. Here's theta, the angle between them. we know that the directional derivative, which is given by this dot product, should be equal to the product of the magnitudes of our two vectors times cosine of theta, where theta is the angle between them. Okay. What to pick on next? Oh, what can we say about the magnitude of v? I think we should be able to say exactly what number that's going to be equal to. What's that? Can you speak up a little bit? I didn't hear you. Oh, you said that that should be 1? Why is that? That's right. We know exactly what this should be, that should be equal to 1, because we said that v has to be a unit vector, and v a unit vector, by definition, just means the magnitude of v, the length of the vector v, this expression, is going to be equal to 1. So we can simplify this a little bit and just write this as the magnitude of the gradient vector evaluated at A times cosine of theta, where theta is the angle between v and the gradient vector. So our directional derivative, we just rewrote as being equal to magnitude of the gradient vector of f evaluated at A, dotted with, or not dotted with, but just times, because that's a scalar value, cosine of theta, which is going to be another scalar value. So when you multiply these two numbers together, that's going to give us the slope of what we would get if we started at A on the surface of F, walked in the same direction that V was pointing. Any questions or comments so far? I'm just kidding. You're all not actually here, so I don't care. Oh, wait. Hold on. I'm actually getting beamed in a message telepathically. Let's see. John, you had a question about how did we know that we needed to take the magnitudes at this point instead of just taking the dot product times cosine of theta? It's a good question, John. That was coming from this formula here, where we really just replaced A and B in this expression. A and B were getting replaced with gradient of f at A and vector v, respectively. So if we replace A and B with gradient vector and v in all of these expressions, this is precisely what that would come out to. Good question, John. Glad you asked. Okay, so now that we know how we can rewrite the directional derivative here, let's see what happens if we try and maximize this expression. Here's the thing. Since we're looking for the vector v, the direction we can travel in, that'll maximize all of this, the gradient of f evaluated at A is just going to be a constant. This is just going to be some constant number corresponding to whatever your function is and whatever point A is. But if all that you're looking at is what direction can I walk in that'll make the directional derivative, this whole expression, as big as possible, this is just good. Whatever we plug in for v is not going to affect this number. It's only going to affect the cosine of theta term. So really, the question we need to ask is, what vector should we plug in for v that will maximize cosine of theta and hence maximize this whole thing? So let's ask which v is going to maximize the directional derivative, which we have seen is going to be equal to the magnitude of our gradient vector times cosine theta. Well, we know something about cosine of theta. We can say, since cosine of theta is maximized when theta equals, better put on the spot. Madeline, what's the largest, what value can we plug in for theta that'll make cosine of theta as big as possible? Keeping in mind, cosine of theta is always going to give us values between -1 and 1. So 1 is the biggest that it can possibly get. What can we plug in for theta that will give us a cosine of positive 1? Good memory, Madeline, that's right. It's at theta equals 0. So we could say cosine of theta is maximized when theta equals 0. That's going to tell us that when theta equals 0, our directional derivative, dv f of a, which is equal to this constant vector, or technically the magnitude of a constant vector, the gradient of f at a, times cosine of theta, is maximized. It's as big as it can possibly get. When theta is 0, that's what's going to be the scenario that's going to cause our directional derivative to be the largest positive number it can be. And that's going to be with a value of, well, magnitude of f evaluated at a times cosine of 0. Well, that's just going to be 1, and then we'll just end up with the magnitude of the gradient vector. So in other words, when theta equals 0, that's going to give us the largest possible value for our directional derivative, which is one of the things we wanted to prove. That when the directional derivative is maximized, when it's as big as it possibly can be, the largest value you can take on is the magnitude of your gradient vector of your function f evaluated at a. Neato burrito. So, let's see. Jared, what can we say when theta is equal to 0? So when the angle between your direction vector v and the gradient of f at a is just 0, if theta is 0, what can we say about the relationship between v and the gradient vector? That's right. There have to be parallel. If the angle between them is 0, then that means v is going to point in the same direction as the gradient vector. And that'll give us kind of the other thing we needed, that our directional derivative is maximized if v and the gradient vector point in the same direction. So if we write that down, we can say when theta equals 0, this means that the gradient of f evaluated at a and the vector v point in the same direction, giving us our result. So that's then finally going to tell us exactly what we need to know. That what direction v can we pick that's going to make the directional derivative as big as possible? Well, that's going to happen if v and the gradient vector are parallel. If they point in the same direction, which we showed down there, and when they do point in the same direction, the value of our directional derivative, meaning the largest value that it can possibly take, is going to be equal to the magnitude of the gradient vector. And that's part A. Elizabeth has a question. Elizabeth, I just heard you ask me, how is this going to be different if we look at part B instead of part A? It's a good question. So part A, we actually proved that the largest value the directional derivative can possibly take is equal to this value, magnitude of the gradient, and that occurs when v and the gradient vector are parallel to each other. How can we prove that that we can minimize the directional derivative if v points in the opposite direction to the gradient vector, in which case the directional derivative is the negative of this? Well, that's actually a very similar proof, and that's one I would like for you all to think about. And keep in mind, I think that would make for a very interesting quiz or test question, how to prove part B of this theorem. So why don't you think about that one, Elizabeth? And if any of you want to talk to me about it, I'd be happy to talk to you in office hours when we get back, or over email. Okay, So let's put this theorem to the practice by looking at an example problem, where we're going to look back at the same kind of example we were doing in class on Wednesday. Where the function f of xy is going to be e to the 2y times sine of x. Our point is going to be at the point pi over 3 comma z. So our f is a function from R2 to R, and our point A is going to be a point in R2. And the question I want to ask is, to start, which direction vector, so in other words, a unit vector v, will maximize our directional derivative, dv f of a. So in other words, wake up. We pull down this screen again for a second. If this is our function, which it is, this is our f of xy, and this is the point right here, what should our direction vector v be that's going to point us in the direction of the most uphill slope? So let's find that out. Well, according to this theorem, the theorem tells us immediately which direction it should point in. V needs to point in the same direction as our gradient vector, the gradient of f evaluated at a. So, according to the theorem, V should point in the same direction as the gradient of f evaluated at a. So let's find that direction. By, first of all, finding what's our gradient vector going to be. So we know what the gradient vector is. The gradient of f at xy is going to be del f del x and del f del y. If our f of xy is e to the 2y times sine of x, Marie, what's going to be our del f del x? That's right. E to the 2y is just a constant. The derivative of sine of x is cosine of x, so we'll get e to the 2y cosine x. And I asked, how about our del f del y? Yup, you got it. This time sine of x is a constant multiple, and the derivative of e to the 2y with respect to y is going to be 2e to the 2y. So we'll get 2e to the 2y sine of x. And so when we plug in our a, which is pi over 3 comma 0, that's going to give us e to the 2 times 0, e to the 2y, times cosine of x, cosine of pi over 3, comma, 2e to the 2 times 0, times sine of pi over 3, which, when we plug that in, e to the 0 is just 1, cosine of pi over 3 is a half, 2 times e to the 0 is just 2 times 1 is 2, times sine of pi over 3, which will be square root of 3 over 2, and that's going to give us 1/2 comma square root of 3. Now keep in mind, that gives us the gradient vector, but we can't let v, we can't just say, oh, the direction vector v that we want to pick, that v needs to point in to maximize the directional derivative is going to be 1/2 comma square root of 3. Avery, why can't that be our final answer? That's right. There's a problem with calling our direction vector this, and that's not a unit vector. We need to make that a unit vector before we can use it. If v is a unit vector pointing in the direction of our gradient vector, then what should v be equal to? Katie, how can we find a unit vector that's going to point in the same direction as our gradient vector? You got it. Wait, what was that? Oh, actually, no, you had a little typo in what you said. Jacob, you want to correct her? That's right. It's going to be equal to the gradient vector of f evaluated at A divided by the magnitude of the gradient vector. Katie, you forgot to say the word magnitude. Sorry, you almost got there. I'm sorry those of you who I'm picking on. We're having a fun time trying to invent your responses that I think you all might make. So this is going to be what our direction vector is. Just take the gradient vector and make it into a unit vector by dividing by its magnitude. So that's going to be 1 over square root of the component, sum of the components squared. So 1/2 squared plus square root of 3 squared times the vector 1/2 square root of 3, which will give us 1 over square root of a 4th plus 3. Square root of 3 squared is just 3, times 1/2 square root of 3, which will give us 1 over square root of 3.25 times a half comma square root of 3, which in the end will give us 1 over 2 square root of 3.25 comma square root of 3 over square root of 3.25. So that is going to be our direction vector v. If this is our direction vector v, that's going to be the direction that we could walk in if we're standing on the surface of f at this point A. That'll give us the most uphill slope, the maximum value that the directional derivative can take at that point. So what is the directional derivative going to be at that point? Well, we can say at this point, directional derivative of f at A in the direction of this vector v. Well, we could go through the process of taking the gradient vector and dotting it with that vector v. But the theorem told us what this is just going to give us. It's just going to be the magnitude of the gradient vector, because the theorem said when v points in the same direction as the gradient vector, the directional derivative, the biggest value you can possibly take, will be equal to the magnitude of the gradient vector, which is going to be this expression right here, which came out to square root of 3.25, which is going to be about, I don't know, let's say 1.8. So you're standing on this surface trying to go uphill as much as you possibly can, you're going to get a slope of about 1.8. Meaning for every unit this way that you go, you're going to go uphill 1.8 units. Olivia, you had a question. Oh, good question. Olivia just asked, what would be the most downhill direction we could go in and the most downhill slope we could get? Yeah, good question. Turns out it's going to be a lot less work to find the downhill direction and the downhill slope. That's as big as it can possibly be, because we can just use the same results we already have and say the most, let's see. If we wanted to say, to minimize, let's say, the directional derivative. We're just going to have v point in the same direction as the negative of the gradient vector, but be a unit vector, which means we could just let our vector v in this case be the negative of the gradient vector divided by its magnitude. And the magnitude of the negative of the gradient vector is going to be the same as the magnitude of just the gradient vector. If you multiply a vector by -1, it's still going to have the same magnitude. We'll just point in the opposite direction. Which in this case will just give us the negative of what we found here, which will be -1 over 2 square root of 3.25, comma, negative square root of 3 over square root of 3.25. So that's, so once we know what the most uphill direction is for v, just take the negative of that to get the most downhill direction. And then the slope in this direction is going to be, well, according to the theorem, it's just going to be the negative of the magnitude of the gradient vector, which is just going to be the negative square root of 3.25, which is about -1.8. So if we were standing at that point on our hill and going as downhill as we possibly can go, we're going to get a slope of about -1.8. So once you know the most uphill direction and uphill slope, you just take negatives of everything and get the most downhill direction you can go in the downhill, most downhill slope. And vice versa. You know the downhill ones, take the negative of that to get the most uphill ones. All right, that's going to do it for Standard 12. But Dr. Gerstel, there's still 2 pages left in this packet of finding tangent planes to implicit surfaces. I decided we're just going to skip all that since we missed a day of class, and I don't want to throw too much on you for something that you could. That's just a virtual lecture. We're just not going to do the last few pages of this packet, and I'm just not going to ask you anything about it. If you want, you can look at my notes when they're posted on Blackboard and see what was going on with those last few pages. But I'm not going to test you over them. You don't have to worry about them. All right, that's going to do it for Standard 11. That's all. That's the last thing you need to know for the exam this coming Wednesday after break. So, hope you're all doing okay. Hope you're all staying safe and enjoying your breaks. When we get back on Monday, we're going to start optimization of multivariable functions, which is a really cool topic. Lots of applications in things like economics, for instance. Hope you all, stay cool, stay snazzy, especially you, Soren. Have a good one.